So let's look at black holes. And before we get into it, I just want to show you, how the gravity of a black hole works. So let's map out the gravity around Earth. So I'm going to click some places and fill in this graph down here. Click. So this graph shows you how strong gravity is as you go further from the center of the Earth. And at the very center of the Earth, you could say that there really is no gravity. Because if you're hovering at the very center of the Earth, half of the Earth is trying to pull you up and half the Earth is trying to pull you down, and they cancel out. But if you move to one side of the Earth, right, gravity is going to seem stronger. It's going to be pulling you towards the middle. And right when you reach the surface of Earth, the gravity is going to be the strongest. So right here on the surface of Earth is when gravity is the strongest, because all the mass is trying to pull you in one direction. And then as you get further away, gravity gets weaker again. Now let me show you how a black hole with the exact same mass of the Earth would be different. Notice the yellow dots appearing? If you're far away from the black hole, the force of gravity is exactly the same. Right? So if a satellite can orbit the Earth out here, a satellite can orbit the Earth out here. But now if you go inside what used to be the Earth, and you're allowed to get closer and closer to that mass, and it's still always on one side of you, so you don't get any of that canceling out effect, gravity can get really strong. So, a black hole is a dense object where the escape velocity exceeds the speed of light. Right? So the speed of light is the fastest that anything in the universe can go. And there are some objects in the universe where that's not fast enough to get away. So here, let's look at this figure. Let's say this is Earth. If you launch a rocket off the surface of Earth and you're going to try to get completely away from the Earth, get away from its gravity, you might need about 12 kilometers a second to get away from the Earth's gravity. So that's pretty fast. If you were launching your spacecraft from a platform that was further away from the gravity, you don't need as much speed. You're already away from some of the gravity. Right? And same out here. You need even less speed because you're already away from the gravity a bit. So let's shrink Earth down a little bit, but it has the same exact mass. Now your spacecraft can be closer to the center, to this denser object here. And so your spacecraft is going to need even more speed, I don't know, maybe 20 kilometers per second, in order to get away from that gravity. But if you go back out here, further away, it's exactly the same. The only difference is going to happen down in here. So now let's compress the Earth even further. So if you're going to launch a rocket off its surface, the surface is down here by this really dense object. So you're going to need a really incredible amount of speed to try to get away from it. But if you're starting from that space platform again, there's no difference, because you're still the same amount of distance away from the center of one Earth mass. So if you wanted to turn this into a black hole, you would just have to squeeze it denser, denser, and denser until this escape velocity eventually just ended up being the speed of light. So I'd like to point out that black holes don't have to be really intimidatingly massive. They don't have to be 1,000,000 times the mass of our sun. They just have to be dense enough that the escape speed is greater than the speed of light. So if the sun was squished down to 3 kilometers, a couple miles, it would turn into a black hole, but it would still be one solar mass and a black hole. If Earth was squished down to only a few centimeters, it would be a black hole. Alright, so let's say you squish the sun down to a couple of miles and turn it into a black hole. Right? Gravity will likely take that mass and keep shrinking it further and further and further down. So that's going to end up being the very center of your black hole is called the singularity. That's where all of the mass of the sun is. But gravity gets weaker as you get away from the singularity, so it gets weaker and weaker and weaker and weaker and weaker. And at a certain distance is where light is allowed to escape again. Right? Once gravity gets weak enough, light is allowed to escape. Right? And that boundary of where light can escape is called the event horizon. Okay? So we can't see anything inside the event horizon because any light that happens from any events in here, it's trapped. The light just gets sucked right back in, down towards the singularity. The event horizon has a radius, and we call that the Schwarzschild radius. Okay? You can orbit a black hole. If you can orbit a star and if you can orbit a planet, you can orbit a black hole. I just wouldn't do it really close to the black hole. Okay? So one thing that your textbook and test banks love to quiz you on is what would happen if our sun didn't have its mass changed at all, but had it compressed down into a black hole? What would happen to Earth's orbit? Nothing would happen to Earth's orbit. Earth would continue to orbit a black hole. Earth would get cold and we would die, but Earth's orbit would be unaffected. If the sun was compressed down into a black hole, right, large orbits are perfectly stable. But if you got too close, like within 6 miles, 10 miles of the singularity, it's not safe. The orbits would not be stable and you would slowly spiral into the black hole. If you had rocket engines, you might still be able to get away until you're inside the event horizon. But if you get close to that event horizon, you're not going to have a stable orbit. In Chapter 4, we talked about tidal forces, basically meaning that the gravity on one side of an object is stronger than on the other side, and it gives you a stretching feeling. So this astronaut here is falling feet first into a black hole. And gravity depends on distance, and so here his feet are closer to the black hole and will feel more pull, and his hands out here will feel the least pull from the black hole. But if you were to ask the astronaut what he feels from his center of mass, it feels like his feet are being pulled down and his hands are being pulled up, so he feels stretched. So this is called spaghettification. If you wanted to fall into a black hole and survive the event horizon, you would choose a high mass black hole. So let's go through this figure. On the left, I have a low mass black hole, and its event horizon here is this circle. Here we have a high mass black hole, and its event horizon is further out. So let's say that you're falling into the low mass black hole. Here you are, you say hi, everything's fine. As you get closer, you start to get spaghettified, you say ouch. You get closer, and at some point you die. The spaghettification would get so strong that you would just die. So for the high mass black hole, you will feel the stretching sooner. Right? I made this guy a little bit further away. But you will make it inside the event horizon before you die. Okay? So it kind of depends on what your goals are. Okay? If you just want to survive the event horizon, pick the high mass black hole and hope that you don't die from something else on the way in. So let's say you're falling into a black hole and you regret your decision and you're going to try to signal your spaceship to come and get you out. So here you are falling into the black hole, and you've got a flashlight. It happens to be a blue flashlight, and you're going to try to signal for help. Flash, 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 come rescue me. But as that light, it fights its way out of that gravity, right, it's going to lose energy. And when light loses energy, it can't slow down, so it loses its color. So if your crew knew that you had a blue flashlight and they were looking for a blue flashlight, they wouldn't see you. Right? That light, when it gets to them, will appear red or maybe even infrared. And if you're really, really close to the black hole, that light might be shifted into the radio. When you're in a strong gravitational field, it can not only affect the color of light, but it can also affect how time flows. And we've proven this with atomic clocks around Earth. Okay. So let's take it one step further and look what would happen around a black hole. So we're going to have two spaceships with clocks on them. And right now they're going to start off at the same distance from the black hole. So the clocks will agree. Right, so I'm going to hit pause here. Right? Confirm here that the two clocks agree. They both say 57 seconds. Now the bottom spaceship is doing something not very smart at all. It's going to burn off some of its orbital energy. So it's going to allow itself to fall in closer to the black hole. Right? As it gets closer and closer and closer to the black hole, its clock is going to lose time compared to the one that's further away. So the closer you are to a big source of gravity, your clock slows down, and that's called time dilation. Alright, now let's talk about the relativity of this. If you were in this spaceship, you would think that your time is flowing normal. You always think that your time is flowing normal. So if you're in this spaceship, you think that this clock is running too fast. And the people in there would also look like they're doing everything too fast. They're taking their coffee break too fast. They're talking too fast. Right? Everything. If you were out here, you would think that your time is perfectly normal. And when you looked at the people in this spaceship, they would look like they were moving too slow. And they're talking too slow, moving too slow, right? Breathing too slow. But you would think that your time is fine. So if you were on this spaceship, you would see yourself fall into the event horizon and eventually die in some horrible way. But if you were in this spaceship watching the other one, you would never actually see that other spaceship cross the event horizon for a couple different reasons. The closer they get to the event horizon, their light is going to get more and more red shifted. So eventually they're just going to become invisible. And second of all, the closer that they get to the event horizon, they appear to be frozen in time. Right? Appear to be. To you. They actually aren't. They did fall into the black hole. But from your perspective, they appear to be frozen in time. Another weird thing that happens around really massive objects is called gravitational lensing. Right? Light tries to travel in a straight line. But if there's a massive object near that light's path, it can actually affect the path of the light and bend it, much like a lens does. Right? So that's why we call it gravitational lensing. Right? This has been confirmed many times out in space. Einstein proved it with the sun during a solar eclipse. We see many different examples of gravitational lensing when we look at different galaxies. Here's a fun example of it. So imagine that you're in a skyscraper and you're looking out at the cityscape. And between you and the cityscape, there's going to be a black hole that passes, just hovering through the air. And we're ignoring that, the atmosphere would get sucked into the black hole and possible other horrible things, but just asking what would happen to the light. And it really just looks like a huge lens passed in between you and what you were looking at. Okay. So somebody took that a step further and used the galaxy as a background and said, how would the light from the galaxy bend around a black hole as we got closer and closer and closer to it? What would it look like? The red grid lines are just for guides. They would not actually be there. And about here, you're falling into the event horizon and you are trapped forever, but some of the light is still falling in with you. We do have a lot of evidence for black holes. Here's a distant galaxy called NGC 4261. It's got some radio jets coming out of it. And if you zoom in and look at the very center of the galaxy, there is a supermassive black hole down in here. And you can look at the orbits of the gas and the pressure of the gas and try to figure out how much gravity is there. And there is something that is 1.2 billion times the mass of our sun. Down in here, in an area that's no larger than the size of our solar system. And we haven't taken a really great picture of it, but what else could it possibly be? Another example is the black hole Cygnus XR1, and there is an accretion disk around Cygnus XR1, and the Hubble Space Telescope watched two blobs of gas detach from the disk and spiral in, getting brighter and brighter and brighter, and if it was going to hit a neutron star, there would be a big bright flare right when it hits the surface, but it just disappeared. So besides a black hole, there's no other way we can explain that. Right, and then you've got the Milky Way's supermassive black hole in its center. Right. So you can zoom into the Milky Way and see some of the innermost stars. And by studying the orbits of these stars going around this object, we can tell that that little cross has a mass of 3.6 million times the mass of our sun. So we say that this is our supermassive black hole. We call it Sag A star. It's in the constellation of Sagittarius, right? So we call it Sag A star. Okay. We've got this massive, massive thing in the center of our galaxy, and we can see things orbiting it, but we can't see it. Right? Occasionally we see a little bit of a flare from this region, and that would be some gas falling into the black hole. Right. Before we start the next section, let's just take a second and review black holes. Right. It's an object that's so incredibly dense that light is not fast enough to escape. Black holes can have any mass. They can be supermassive, they can be the mass of the Earth. You can orbit a black hole as long as you're not too close. And the really extreme gravity can do some really interesting effects. It can redshift light trying to escape from near the event horizon. It can bend the path of light. It can slow down clocks. And it can spaghettify you. The last section is on gamma ray bursts. We won't spend too much time on them. Gamma rays are the most energetic light, and they're only going to come from really energetic objects out in space. And so these bursts of high energy light were discovered in the 60s by US satellites looking for nuclear bomb testing on the ground. We were trying to spy on our neighbors, but we ended up discovering gamma rays from space. And these events seem to be hundreds of times brighter than a supernova. So these events are enormous, 100 times more powerful than a supernova. And they don't come from our galactic disk. And we can see that from this map here. So this map is an all-sky map, and it would wrap around you. And if this was coming from the disk of our galaxy, we would expect most of the dots to line up along the plane here. But they're evenly distributed over the whole sky. So that leads us to believe that they come from other galaxies. There's two types of gamma ray bursts. We call them long and short. Okay. Some people like to call the long gamma ray bursts hypernovas, but that just seems like extra terminology to me that we don't need. Our best understanding of the long gamma ray bursts is that it comes from a supernova. Right? But I just told you that these appear to be hundreds of times more powerful than a supernova. So we think that some supernova, when they collapse, might form a jet. Right? And if that jet is pointed at Earth, we're going to get an extra beam of energy. So it's going to look extra bright. Unlike the long gamma ray bursts, which are maybe 30 seconds long, you have short gamma ray bursts, which are less than a second. And our best guess for what's causing the short gamma ray bursts are possibly a neutron star falling into a black hole. Okay. So a neutron star might be orbiting a black hole. The spaghettification will rip it apart. It will spiral in, losing angular momentum through the accretion disk. And while a lot of the energy is getting sucked into the black hole, the magnetic fields will be able to divert a little bit of energy out the poles. And so we might see that energy coming out the poles as a gamma ray burst. The other option is, what if it's coming from two neutron stars that are colliding? And so you have two really massive objects. And as they're getting closer and closer and closer together, they're losing gravitational potential energy. And some of that gravitational potential energy is going to go in kinetic, and you might get this huge beam of energy that we might see as a gamma ray burst. So there's a bit that we don't yet understand about gamma ray bursts, but we've got the Fermi Gamma Ray Telescope working on it, so give us a few years. We'll see what we can tell you then.